Good afternoon, everybody. Hello.
Good afternoon, sir.
Yeah, good afternoon.
Good afternoon, sir.
Good afternoon. Good afternoon.
Good afternoon, sir.
Good afternoon, everybody. Let us just wait for another 2, 3 minutes more because as of now, the strength is only 14 in a class of about 100 students. This is being the first class for this semester. I hope some more will join. Okay, it's 4:18. Anyway, let others join because we cannot wait for others for a long time. Once again, welcoming into contact session 1 for the subject linear algebra and optimization for this semester starting today. And many of you might have studied the very first topic or first chapter contents like matrices and its nuances in your school days, particularly towards the end, like in 10th standard, 11th standard, or even plus two, something like that. But still, it's a kind of recapitulation and to have a more understanding of matrices later on in the next session, determinants, and so on. And you will also be exposed to linear system of equations, solving them, and which of them are consistent and inconsistent through finding ranks of matrices. So all these things are going to be taught to you today in this context section 1. So with this introductory remark, let me also introduce to you being the first session. I'm Dr. V. Srinivasan, a retired professor of mathematics from a premier university in Chennai, having about 40 years of teaching administrative and about 2 decades of research experience. And my association with WILP, Work Integrated Learning Program Division of BITS Pilani University, for about 18 years now. And my association in particular with the students of HCN is about, I think this is about third year, something like that. I'm teaching LAO about fifth time something. Therefore, with this brief introduction, so let me go deep into the details of our contents of the chapter 1 or lecture 1. Well, as you know, the nomenclature of your subject title, shortly known as LAO in detail, linear algebra and optimization. In the sense, it has got two important parts, linear algebra and optimization. Algebra, you might have studied, and linear algebra, as we are going to study in detail in this semester. And in the second part, you are going to also be exposed to optimization techniques, that is, operations research techniques. And you know very well what is meant by an optimization. Anyway, that we will take it up later. So in linear algebra, in fact, gone are the days when people used to talk about algebra analysis and all those things. That what applications do they have? And remember now that everything is digitized, and India is leading the world in such digital transactions. Even the very developed countries like Germany, Singapore, and many other European countries are still far behind, trailing behind when compared to digital transactions that are taking place in such a big country with 146 crores of people. So why I am talking about this is this cryptography, which was the mother of all these inventions, was really based on your linear algebra. And whatever you have today, AI, artificial intelligence, and again we have come back to this data science, data analytics. So all those things are actually stemming from your basic, rather pure mathematics, important branches such as algebra, analysis, and so on. So coming back to this linear algebra, you are given two textbooks, one for engineering part, linear algebra, Erwin Kreisig, Advanced Engineering Mathematics, and Taha, Operations Research. Reference books are also there. Anyway, after every session gets over, this PPT slides contents will be published in your MS Teams for your reference. Is it clear? So where you can see, especially this being the first session, everything is there, that the textbook, reference book names, and course objectives and all those things. Modules that are going to be covered in 16 sessions for this semester. So what is the content structure or course structure, which are spread over 6 modules we call matrices, vectors, determinants, matrix eigenvalue problems, numeric algebra, modeling with LPP, linear programming problems. First with the graphical method, and then we have different methods, the simplex method, dual simplex method. There are many. And finally, we will be ending with the transportation model and its variants. So the first 3 modules are devoted to the study of linear algebra, and the remaining 3 are devoted to the study of OR, optimization, of operation research or optimization techniques. Okay, so to start with, we have today from module 1, matrices. So what we are going to have in this session, matrices, basic definition, their types, the special matrices, then matrix operations like addition, scalar multiplication, matrix multiplication, and so on. Then we will be finding our echelon form of a matrix, which gets reduced, which will be put to use to find rank of a matrix. And making use of rank of a matrix, we will go for checking whether the system of equations, linear equations, are consistent or not. Yes, somebody wants to say something or any crosstalk? KK, you want to say anything? Your mic is on. Kindly switch off your mic unless you want to say something. Okay. Otherwise, it will be a nuisance to the proceedings. Okay. Matrices. You all might have seen many a time, you might have undergone the easiest topic of linear algebra. It is an array of
Sir, still you are not
numbers.
audible.
Yes. KK? Yes? Hello?
Oh,
Yes? You are trying to say something. What is that? Am I audible or not? Hello?
You're audible, sir.
Audible? Yeah, fine. Okay. So matrix is an array of elements in general, which may be alphabets, which may be numbers, which may be letters, which may be functions, etc. Anything can be arranged in terms of rows and columns, which are normally set without any commas in between and then enclosed within brackets, which you are all must be knowing. For a simple example, you just look at the first matrix, x1, x2. Vinil Kumar, you have written, I'm not audible, but somebody says I'm audible. Am I audible or not?
you are audible, sir.
Yeah,
You're
fine,
audible.
good. Okay, okay, good. Okay, so just look at this. So immediately somebody will think that by just having x1, x2, x3 with the brackets, it doesn't look like a matrix. Is it a matrix, sir? Because normally, whenever you are seeing a matrix, whenever you are writing a matrix, you will be writing numbers. Okay, leave alone that, because practically you might have seen in your school days like that, doing addition, subtraction rather, scalar multiplication, all those things. But you can write even alphabets, you can write elements, you can write alphanumeric, everything. But ensure that there is enough space between to ensure to make it sure that you have rows and columns. So here you have rows, but only one row. But there are three columns which we are going to talk about in detail. What does what is the nomenclature? What is the title? Or what is the name of such a matrix? Well, we will be calling it as a row matrix, irrespective of the number of columns. Of course, irrespective of number of columns means not infinite. It's everything is finite here. So, irrespective of the number of columns, it can be three or four or two. If you have one row, it is a row matrix. Similarly, irrespective of the number of rows, if you just have only one column, it's going to be called a column matrix. So these are all going to be taught under special matrices, isn't it? So here it is also a matrix. X1. So don't put comma. If you put x1, comma x2, comma x3 within ordinary bracket, then it will become ordered three tuple. It become a point in space. And then we will be going to an element in vector space, all those things that you will be dealing with in the next session. So as of now, when you have elements arranged in terms of rows and columns, here also rows and columns, there is one row, but there are three columns enclosed within ordinary brackets or square brackets. Both are okay. Go to the next one. You have four half. There are two rows, only one column. In fact, it is called a column matrix. Look at the elements here, but normally we don't put fractions as element, but nothing wrong in it. Even if it is there, nothing wrong. We will put 0.5. Okay, nothing wrong in it. You can put fractions also. So the second matrix is an example of a column matrix where you have two rows and only one column. In the sense, how do you read it? First row, first column is 4. Second row, first column is your half. So it is there is only one column, but there are two rows. So it is a column matrix. The first one you had first row, first column, element x1, first row, second column, element x2, first row, third column, element x3. That means it is there is only one row, but there are three columns. So it is a row matrix. So later on, we are going to talk about order of your matrix. That will put you in good stead to know more about exactly. We talk about the types of matrices, everything. You look at the third one. You have two rows and three columns. Well, there are you are having positive integers, negative integers, zero. Anything can be, any number can be an element. Go to the third one. You have functions. E power minus x, exponential function. X power of minus x is a function. X square is a function. E power 6x is another function. 4x is a function. So here you have elements of the matrix to be functions. That's the reason why in the the first definition, it's mentioned there, it is an array of numbers or functions. Go to the last one. You just have general entries of a matrix. Always it will be looking like this. You can easily identify that any element in any matrix that you are going to do in practice, you will be identifying them with A11, A12, A13, A21, A22, A23, A31, A32, A33. That is, there are two subscripts. First denotes the row position, second denotes the column position. So what do you mean by A11? First row, first column. A12, first row, second column. A13, first row, third column. Similarly, second row, third row. And so you have there three rows and three columns. And here are entries with the subscripts. So you are able to see how a matrix can be coined, how a matrix can be written. So the numbers or functions are called entries or in general elements of the matrix. More often we will be using the term elements of a matrix. And in particular, we can also refer them to entries of a matrix, as I just mentioned, such as A11, A12, A13, because when you are going to write a matrix, it is going to be, the matrices are going to be generally represented by capital letters, uppercase, that is capital A, capital B, capital C, etc. And the elements entries for capital A, normally we will put small a, suffix subscripts I, J. I stands for the position of the row, J for column. So Aij, I equal to 1, 2, 3 means first row, second row, there are three rows. J equal to 1, 2, 3 means three columns. So here, instead of writing A11, A12, A13, A21, A22, A23, A31, A32, A33, you can simply mention it as small a, subscripts ij, enclosed within brackets, and write I, comma j equal to 1, comma 2, comma 3, or 1 to 3. So this is another way of representing matrix. Capital A is equal to, this is how we are going to later on represent them in quickly. Okay. It can be small aij or xij or mij. Suppose you put the matrix as capital M. So these are all just notations. Okay. Matrices are denoted by, as I just mentioned, capital, boldface letters, that is uppercase, A, B, C, etc., or by writing the general entry in brackets, which I just have mentioned. A, J, K, or A, L, M, or I, J. Normally, we will be using subscripts J, K, or I, J, or M, N. Nothing wrong. Any letters are used, but in practice, you will always be using. So some letters are always standardized, reserved, which will be put to use. We will be putting into use. Now, next we go for order of a matrix. So order of a matrix is nothing but number of rows into number of columns. Your symbol is into multiplication symbol, but you will not be reading it as m into n. Supposing there are m rows and n columns, you will not be reading it as m into n. You will be reading it as m by n. But by, we don't mean it is divided by. This by, we mean multiplication. This is something like, so you take any plane or any notebook, any two dimension, or any room you take, you will immediately be asking for what are its dimensions. You say it is a 10 by 10 room. What do you mean by 10 by 10? Length or breadth, one is 10 feet, another is 10 feet. Isn't that? So one can be 12 by 10, breadth can be 12, length can be 10, and length can be 12, breadth can be 10. The two dimensions are length and breadth. You will have to mention which is length, which is breadth. Otherwise, they are just a dimension. 12 by 10 means 12 feet into symbol 10 feet. So that into helps you to find the area of the room. I mean, the plane, the wall, or the floor, isn't it? So you say it is 10 by 10, 10 into 10 equal to 100 square feet. Its area is 100 square feet. 12 by 12, 144. Same way here, if you suppose you take any plane or any notebook, something like a two-dimension, you say that what is the uh, dimension? So it is 3 by 3, maybe centimeter or in inches, say 3 by 3, 3 inches by 3 inches. So the area is 9 inches. Same way here, it is not about the area, but to find the number of elements of the matrix without doing actual calculation. If there are m rows and n columns, then m into n would mean the number of entries of the matrix. Just look. By an m by n matrix, so read it as m by n. Don't read m into n, but put the symbol into to mean it is multiplication. Okay. Read, as I just now mentioned, m by n. But by doesn't mean divided by. Okay. So read m by n matrix. We mean a matrix with m rows and n columns. Okay, rows always come first. Okay. M by n is called the size of the matrix. It's actually order of the matrix. More than the word size, normally we'll be using the word order of the matrix. Order of the matrix is the most widely used usage. Thus, an M by n matrix is of the form. How does it look like? We just have seen capital A is equal to small a jk within square brackets. If you expand it with j equal to m number of rows, k equal to n number of columns, you can write it in full a matrix enclosed within square brackets or ordinary brackets whose entries are a11, a12, etc. a1n, because first row, first column, second column, nth column. There are n columns. Then a21, a22, etc. a2n, second row, first column, second column, nth column, etc. etc. am1, am2, etc. amn. So mth row, first column, mth row, second column, mth row, nth column. So that how many elements are there now? Mn. Right? Suppose you have 2 rows and 3 columns. How many elements will be there? 2 into 3, 6. Look at. We are going to introduce a term here, vector, when you are having the special type of matrix like row matrix or column matrix. Such matrix, of course, you can regard them as row matrix, you can regard them as column matrix, but still, when you have them as a row matrix or column matrix, the special name that we will be giving them is a vector. Okay, right. You might have studied vector calculus, vector analysis, but here in matrix parlance, in linear algebra, and later on, when you are going to have in the very next session about vector space, we will be dealing with vectors. So it is it's a kind of prelude in matrix that when you have row matrix as well as column matrix, they can also be regarded as vectors. Just look at it. A matrix with just one row, irrespective of the number of columns, which I just mentioned earlier, is called a row matrix. Similarly, a matrix with just one column is called that means irrespective of the number of rows, understood, is called a column matrix. Matrices having just a single row or column are also called vectors. Okay. Row vectors. A. See here, you can look at on the left hand side, the notation, even though it is a matrix, which we normally write by uppercase alphabets, when you are taking up row vector as row matrix as well as column matrix, which are also called, especially called as vectors, we can put, you know very well, the vector symbol. You can even write a small or lowercase alphabet and you can put an arrow mark on the top, because you know very well a vector is a physical quantity which has got both magnitude and direction. Isn't it? So normally vectors are usually represented by lowercase alphabets with an arrow mark on overhead. But in practice, writing overhead, sometimes we will avoid, we will just put bar to mean it's a vector. Or sometimes even if you don't put bar, you will bold it. You just look at this one. Just look here. Look this. Instead of writing A, see these are all various ways of writing your vector that you are going to deal in detail in the next session under the caption vector space. So you will write small letters to mean vector, and you will put here an arrow mark to mean a direction, because vector is a physical quantity having both magnitude and direction. Otherwise, it becomes only a scalar, isn't it? So instead of writing in detail the arrow mark, you can also as well write a shorter form of putting a, just a bar. Okay. And even that can be avoided. You can put a, but you have to bold it. If you are not putting the bar or arrow mark, you have to bold it. Isn't it? So these are all various ways of representing a vector. So here, even though here it is a matrix, being a row matrix or a column matrix, you can regard them or you can represent them as a vector with a bold letter, or you can even put even arrow mark on this bar. So A1, A2, some other alphabet here. Okay, AN. Then A here, of course, full of numbers. Here, negative integer, positive integer, zero, and here you have a decimal. All these things are possible. So these are all just examples. Its entries are called the components of the vector. So when it is being specially called a vector, then as instead of saying entries of a matrix, you just say call them as components of a vector. So for column vectors, you take just denoted by B, bold B. Its entries are column, one column, B1, B2, some alphabet, capital M, then BM. Then B, vector B can also be having numbers like this. Okay, positive integer, zero, negative integer, and so on. So any a matrix of any size n by n is called a square matrix, and any matrix of size m by n is called a rectangular matrix. In the sense, M and N are unequal. Length and breadth are not equal. Then you call it as a rectangle, isn't it? A geometric shape. So similarly, here when M not equal to N, that is when N, the number of rows not equal to number of columns, such a matrix is therefore called a rectangular matrix. In the same fashion, when length is equal to breadth, then it becomes a square, isn't it? So here also the same way, when M equal to N, that is, the order becomes n by n or m by m, both are one and the same. And the numbers are the same. Then such a matrix will be called a square matrix. And remember, basically, we will be dealing with rectangular matrices, square matrices, etc. But when you go for special matrices such as unit matrix, zero matrix, that is null matrix, and any special matrices that are being considered will only be square matrices in general. Okay. Now, we go about talking the equality of matrices. What do you mean by equality of matrices? They, of course, the very word suggests that when you say the two matrices are equal, then the corresponding entries are equal. In the sense, they must be of same size. Then only you can think of the corresponding entries, and they are also the same. Okay. Two matrices A, AJK, and B, BJK are equal, written A equal to B, if and only if, as I just mentioned, they have the same size. Size here means order, and the corresponding entries are equal. That is A11 equal to B11, A12 equal to B12, and so on. Here, let A equal to a matrix having entries A11, A12, A21, A22. That's a square matrix which is of order 2 by 2. You know, you can have many square matrices of different orders like 2 by 2, 3 by 3, 4 by 4, and so on. Here is a square matrix with elements A21, A11, A12, A21, A22, and B elements are integers. Okay, then A equal to B if and only if A11 equal to 4, A12 equal to 0, A21 equal to 3, A22 equal to -1. Right. Matrices that are not equal are called different matrices. Okay. Thus, matrices of different sizes are always different. Okay. So here you can see a matrix of order 2 by 2. Here also you have a matrix of order 2 by 2. But what's happening? Even if the sizes are the same here, naturally when they are of different sizes, they will not be equal. Even if you are having matrices of same size, but the corresponding entries are not equal, means they are not equal, is it not? We will go for now algebra of matrices. In the sense we will be making use of operations on matrices. Addition, when addition is there, the same way subtraction will also follow. Of course, scalar multiplication, then you have matrix multiplication. Remember, there is no division of matrices. That is to be borne in mind. Okay. So we have not specifically mentioned here addition, of course, addition, but not subtraction. We have special scalar multiplication, we have product or multiplication. Because so when you have the addition, the same way you can have the subtraction. That means whenever two matrices are to be added, or one matrix is being subtracted from the other, first thing is that they must be of same order. Second thing, corresponding entries are being added for addition, and the corresponding entries will be subtracted from the other one. Is it right? And therefore, that is subtraction. That is automatic. So, addition or sum, SUM. The sum of two matrices A and B of same size, that is same order, is written A plus B and has entries AJK plus BJK, obtained by adding the corresponding entries of A and B. Matrices of different sizes, different orders cannot be added. But remember, this is the case with the subtraction of two matrices also. But for multiplication, orders of the matrices can be different. But still multiplication is possible, unlike addition and subtraction. For addition subtraction, they must be of same order. Then only we can have the corresponding entries being summed up for addition, or one is being subtracted from the other in the corresponding way. But when it comes to multiplication, that is product of two matrices, they can be of different sizes, but there is one condition. Only when that condition is met, satisfied, you can think of the definition of product, or the product of two matrices being defined. Okay, before we go to the product, let us simply have first scalar multiplication. What do you mean by scalar multiplication? A scalar, a constant being multiplied by a matrix. How is it possible? It is possible that every entry of the matrix will get multiplied by that single constant. That's what we mean by scalar multiplication. Just look at the next. The product of any m by n matrix A and any scalar, a number C, is written C into A. C is your scalar, that is a constant, and the matrix is the m by n matrix. It's going to be the same order. Order will not get changed. So what will happen to that C? It gets multiplied by every entry of the matrix A, so that it becomes CA. So CA, what will be the entries then? C into AJK. That's all. Obtained by multiplying each entry of A by the single constant C. We are going to see examples. Next. Rules for matrix addition and scalar multiplication. A plus B equal to B plus C. You know very well, addition of two matrices is commutative. Commutative means any order you take, either A first, then B, or B first, A, then addition is going to be the same. And because it is going to be the same order, if it is 2 by 2 plus 2 by 2, then you got the resulting matrix will also be 2 by 2. So if any order you put, it is going to be the same, even if you reverse the order. In other words, you can say it is commutative. Addition is commutative. Then A plus B plus C is same as A plus B plus C. So you are here first finding addition of two matrices, and that single matrix is being added to another matrix, so that you have addition of three matrices, which is the same as A first, and then addition of those two B and C. It is, you know very well. What is it called? Can anyone say what property it is called? Can anyone? Hello? Vishal? Hari Gayatri? Hello? Is there anyone to respond? Hello?
Sir, is it associative?
Very good. It's called associative property. So you might have seen all these things in your group theory also, isn't it? Okay. Then A plus 0 equal to A. But it is not 0 here. 0 means actually cap O. Cap O means 0 matrix. You just can add an integer with A. You can multiply a constant by a matrix. That is, every entry of the matrix gets multiplied by that constant, single constant. But you can't add any integer with any matrix. You can add 0 matrix. That is, suppose you have a matrix A of order 2 by 2 with some integers, non-zero. And then you have 0 matrix. You have suppose 2 by 2, 0, 0, 0, 0. Then you can add the corresponding entries. Corresponding entries. They must be of same order. But A plus 0 means here, what does it mean? So you cannot add. Of course, you can multiply constant 0 with A. What will happen? Every entry will become 0 so that the matrix becomes A becomes 0 matrix. But here it is the matrix A added to, it is not integer 0, it is 0 matrix. Remember, this is actually to be taken as O, cap O. This is actually to be taken as, we consider as cap O. It doesn't look. Okay, so I just always write this to mean zero matrix. Zero matrix. It is represented by naturally cap O. Isn't it? So A plus 0 equal to A plus O equal to A. A plus minus A equal will naturally be equal to O. It is also zero matrix. Also zero matrix. Zero matrix. Okay. So here again, C constant into A plus B. It is CA plus CB. Okay. Then C plus K into A. It is CA plus KA, distributive, isn't it? C into KA is nothing but CK. Constant gets multiplied with the constant, and that gets multiplied with the matrix. So CK into A. So for the constant, when it gets multiplied, you don't need to put any bracket. So you can simply written CKA. Okay. Something like your constant, some constant say P, whatever it is. So that is your CK. This is actually I A is equal to A. It is not again integer 1. So this is actually capital I. This is actually unit matrix. Unit matrix. So suppose you take a 2 by 2 matrix. What will be square matrix? Remember, as I mentioned earlier, special matrices such as zero matrix or null matrix and unit matrix are all only square matrices. So what is the unit matrix? What will be its elements? Principal diagonal elements will be all 1 and remaining elements will all be zeros. Isn't that? You must be knowing capital I is equal to 1, 0, 0, 1. Suppose you have a 3 by 3 matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. So here, some of us will be committing mistake by just remembering that diagonal elements are ones and others are zeros. They will write 0, 0, 1, 0, 1, 0, and 0, 1, 0, 0. Anyway, there are ones in the diagonal. No, remember the ones are taking the place of principal diagonal. As you know very well, you have two diagonals. One is principal, main, primary, and the other one is secondary. Isn't it? So you have to have the principal diagonal, which means starting from first element to the last element. So they all should be equal to 1, and the remaining element should be zeros. You know very well what is I unit matrix. And zero matrix, 0, 0, 0, 0, 0, 0, 0, 0, 0. If it is a 3 by 3 matrix, if it is of order 2, 2 by 2, 2, 0, 0, 0, 0. Denoted by cap O, as any matrix is being represented by uppercase alphabet O, something looking like 0, so it is chosen. So similarly, I, it is for your unit matrix. Okay. So here, yeah, as I mentioned, cap O denotes zero matrix. That is m by n matrix with all entries 0. Actually, it is of size m by n, means it is a m equal to n equal to n. So it can be 2 by 2, it can be 3 by 3, anything. These are only square matrices. And a multiplication of a matrix by another matrix. The product C equal to AB in this order. In the sense, A first, B next. You can have BA also, but here we are taking why that what is so special about the order is there. That is very important in matrix multiplication, which many of you might be knowing. And again, we'll see now. In that order of A followed by B. So we are finding product of A and B, and that we can of course regard it as some capital C, the resulting matrix. Okay. Now AJK times, that is being multiplied by M by N matrix A being multiplied by an R by P matrix B is defined. That is such a product is defined if and only if R equal to N. What is R here? What is R? You just look at here. N. Just look at here. So, okay. So what's the meaning? Number of columns of the first matrix should be the same as number of rows of the second matrix. That is what it means. So unlike addition and subtraction of two matrices, the orders of the two matrices for product need not be the same. If they are one and the same, well, very good, fine. It is quite obviously defined. If they are of different orders, still product is possible provided this condition is satisfied. That is, number of columns of the first matrix is the same as number of rows of the second matrix. In such a case, what will be the order of the resulting matrix? The number of rows will be number of rows of the first matrix, and number of columns of the second matrix will be even number of columns in the resulting matrix. Okay. So if R equal to N, that is important. Okay. And is then the M by P matrix C with entries CJK equal to summation AJL into BLK, where L runs from 1 to N. If you really go, if you just go through the theory, you might be wondering what does it mean. It is nothing but AJ1 B1K plus AJ2 B2K plus AJN BNK. So that your number of columns, the column position of A and the row position of B must be the same. That's what it means. And you can rotate J, the rows from 1 to M, if there are M rows, is it M rows? And your K column is from 1 to P, because your resulting matrix CJK will be of order M by P. So the condition R equal to N means that the second matrix B must have as many rows as the first matrix A has columns. That is, in short, number of columns of the first matrix should be the same as number of rows of the second matrix. Okay, so that's what it is written. A is of order m by n, B is of order n by p here. So you can, these two are equal. Therefore, the resulting matrix, product matrix, will be of order m by p. Addition of matrices and vectors in the sense when there are row matrices and column matrices. We just look A, B. What is A plus B? Corresponding, see, this is of order 3 by 3. This is also of 3 by 3. So first condition, they are of same order. Corresponding entries are to be added. So A plus B equal to minus 4 plus 5 plus 1. 6 minus 1 plus 5. 3 plus 0, 3. 0 plus 3, 3. 1 plus 1, 2. 2 plus 0, 2. Scalar multiplication. If A equal to this 3 by 2 matrix, this is a rectangular matrix, no matter, no problem. There are 3 rows and 2 columns. Then what is minus A? That means you are multiplying A by minus 1, a scalar, a constant. So every entry will be multiplied by minus. Minus 2.7, minus 1.8. We don't put minus 0, 0, minus 0.9, minus 9.0, plus 4.5 because there is already minus. Next, if A equal to this much, we want to find CA. What is C here? Constant? 10 by 9. Isn't it? So every entry is multiplied by 10 and divided by 9. That is 2.7 into 10, 27, divided by 9, 3. 1.8 into 10, 18 divided by 9, minus 2. Of course, minus is there. Like that. Okay, this you can see. Every entry of matrix A gets multiplied by 10 and divided by 9. 0A. Here scalar, this is integer 0. This is your C, constant C. It is not cap O. You cannot multiply a matrix with 0 matrix here. Okay, but it is integer 0. So what is happening then? It is the integer 0. So every entry of A gets multiplied by 0. So you get 0, 0. You get 0, 0, 0, 0, 0. Next, matrix multiplication. Just look at here, multiplication of a matrix and a vector. Actually, it is multiplication of two matrices. One is matrix of order 2 by 2. Another one is also a matrix of order 2 by 1. That is a column matrix. That's why it's called a vector. And so it is written as multiplication of a matrix and a vector. Anyway, idea is going to be the same. It is something like your multiplication of two matrices. So what is the first condition? Whether the product is defined, whether the multiplication is possible for this example, you have to check. This is of order 2 by 2. This matrix is of order 2 by 2. And second matrix is of order 2 by. So number of columns of the first matrix is the same as number of rows of the second matrix. Therefore, your result, therefore the product is defined. Multiplication is possible. And the resulting matrix will be of order 2 by 1. That means you will have only a column matrix. That is a vector. Why? You just check, you'll be able to. And how you do the multiplication? Using that formula sigma, the product. Why? How do you do the product? How do you do the multiplication of entries? You have, it is not like addition, subtraction, the corresponding entries, but it is first you have to take the first row, multiply by the corresponding column elements, and then add them up. Multiply elements of first row fix and multiply the corresponding entries with the first column and sum them up. What is the meaning here? 4 into 3 plus 2 into 5. That's all. Don't write this as 4 into 3 space 2 into 5. It is 4 into 3 plus 2 into 5, a single element. Next, second row, come to second row. Repeat the process now. 1 into 3 plus 8 into 5. Isn't it? This is the process. So what do you get? 12 plus 10, 22. 3 plus 40, 43. So you just have only 2 rows and 1 column. Then only you are correct. Suppose by mistake you write 4 into 3, space 2 into 5, space 1 into 5, plus 8 into 5. No, plus 8 into 5. Then you will get 2 by 2 matrix, which is wrong. Is it right? Right. Whereas if you do the multiplication, that is, this is suppose something like AB. Suppose you take this as AB. AB is defined. Correct. It is of order 2 by 1 resulting matrix. Whereas you take BA. What's happening? B is 3 by 5 matrix. A is 4, 2, 1, 8. And what is happening? This is of order 2 by 1. B is of order 2 by 1. A is of order 2 by 2. Is the product defined? No, because the number of columns of the first matrix is not the same as number of rows of the second matrix. Therefore, the product is undefined. Is it clear? Is there any doubt? Hello?
No, sir.
Okay, fine.
No, sir. Yeah.
Okay, good. Now, just see that this is again, this is a vector, this is also a vector. This is a row matrix, this is a column matrix. The same thing, 3 into 1. So, this is 1 by 3, 1 row, 3 columns. So, it is 1 by 3. This is 3 rows and 1 column. Just look at this is 1 by 3. And this is of order 3 rows and 1 column. So here number of columns, number of rows are the same. Therefore, the resulting matrix will only be of order 1 by 1. What is 1 by 1? It is a one row, 1 column. That is a single element. It's a single element matrix. Don't simply put 19, but put 19 within brackets. That is, it is a matrix, but with only 1 element. Because why? How did you get this? You just check 3 into 1 plus 6 into 2 plus 1 into 4. That is 3 plus 12, 15 plus 4, 19. So it is also a matrix. How many rows are there? 1 row. How many columns are there? Only 1. So it is a single element matrix. Okay. So similarly, you can find out here. Here, this is of order 3 by 1. Just look at the beauty of the orders. That is very, very important. This is of order 3 by 1 and this is of order 3 by 3. Isn't it? I mean, this is of order 1 by 3. Look at 1, 2, 4 vector column matrix is of order 3 by 1. 3 rows, 1 column. This is row matrix. That is 1 row, 3 columns of order 1 by 3. So your number of columns of the first matrix is the same as number of rows of the second matrix. Therefore, you have the product defined. And what is the order of the resulting matrix? It is 3 by 3. Just look at number of rows is 3, number of columns is 3. So you must get a 3 by 3 matrix. That is possible. How? We just check 1 into 3, 3. 1 into 6, 6. 1 into 1, 1. 2 into 3, 6. 2 into 6, 12. And 2 into 1, 2. 4 into 3, 12. 4 into 6, 24. 4 into 1, 4. So you get a 3 by 3 matrix. Next. This is the usual way of our multiplication finding between two matrices of different orders. Okay. So here it is of order 3 by 3, but here it is of order 3 by 4. So this is of order 3 by 3. This is of order 3 by 4. Number of columns of the first matrix A is 3. Number of rows of the second matrix is also 3, even though the number of columns of B is different, that we don't bother. So we have here 3 by 4, 3 by 3. Here we have 3 by 4. So the product of these two matrices A and B is defined. So what will be the order of the resulting matrix? What will be the order of the matrix AB? 3 number of rows of the first matrix A, 4 number of columns of the second matrix B. How do you get? Just check. First you fix the first row. Take the first column. Okay. 3 into 2, 6 plus 5 into 5, 25, 31 minus 9, 22. Fix the same first row, go to second column. 3 into minus 2, minus 6, plus 0, plus 4. You get minus 2. Same first row, go to the third column. 3 into 3, 9, plus 5 into 7, 35, 44, minus 1, 43. Go to the last column. 3 into 1, 3, plus 5 into 8, 40, 43 minus 1, 42. Now repeat the same process with the first column, second column, third column, and fourth column, corresponding elements of the second row. Sum them up to get second row elements. Same way, third row. So it is just shown. C11, that is first column element, is 3 into 2 plus 5 into 5 plus minus 1 into 9, 22. The entry in the box is C2, C23. Box means this is just shown you, just to identify. C23, because this is a second row, third column element. How did you get? So it is shown in blue color, just identification. 4 into 3, 12, plus 0 into 7, 0, plus 2 into 1, 2. So it is 12 plus 2, 14. So this is how it is explained now in detail. The product BA is not defined. So it is for you to take it up as an assignment, in the sense you can try your concept right from the beginning. You don't need to wait for just the title, that assignment. There are these other questions. Before that also, you can always, whenever you find time, you can check all these things. So the product BA is not defined. Why? You can immediately say it is not defined because this is of order 3 by 4. This is of order 3 by 3. So the condition is not met. Therefore, the product is not defined. Matrix multiplication is not commutative. That is AB not equal to BA in general. Very rarely you may get them to be equal, but in general, they are not equal. It's not commutative. Okay, so here is an example. You can check A and B. AB is found 0, 0, 0, 0 matrix, but BA is something different. So in general, they are not equal. Now, this, of course, we already seen. K, A, you have a scalar multiplication multiplied by B is K times, is same as K times product of these two matrices is also equal to A into KB. So if you remove brackets, it is nothing but KAB or AKB, where K is a scalar. Same whatever is you had for your some addition, the associative property A into BC equal to AB into C. This is multiplication properties written ABC without any bracket, because you are going to get only one matrix. A plus B into C, this is distributive now. A into C plus B into C, you can check. Also C into A plus B, C A plus CB. So you can find, supposing you are given three matrices A, B, and C, you may be asked to prove A plus B into C equal to AC plus BC. So these are very preliminaries. So A, you will find A plus B first, multiply with the C. That is equation 1. You will find A into C, you will find B into C, you will add them up, you will find the resulting matrix should be the same. So it may be also noted that AB equal to the product of two matrices equal to cap O, very rarely you may have. See, you are having, depending upon the numbers, you may have product of two matrices to be a zero matrix. The entries of each of the matrices might be non-zeros, but still, you just see here, 1 into minus 1 plus 1 into 1 minus 1 plus 1, 0. 1 into 1 plus 1 into minus 1, you get 0. 100 into minus 1 plus 100 into 1, 0. 100 into 1 plus 100 into minus 1, 0. So the product of two non-zero matrices can still be a zero matrix. But it does not necessarily imply that BA equal to 0. That is 0 here means 0 matrix. Or A equal to 0 matrix or B equal to 0 matrix. So look at here again. A is not a 0 matrix, B is not a 0 matrix, but still the product is 0. But AB is a 0 matrix, doesn't guarantee that BA is also 0. Well, so we will continue after 5 minutes break, shall we? Hello? Further
Okay, sir.
Yes,
properties
sir.
of
Sure.
matrix. Hello?
Yes, sir.
Okay, sir.
Yes, okay. Right.
Okay.
Hello. Shall we continue? Are you ready?
Yes, sir.
Okay, right. So transpose of matrices and vectors. Transpose of an m by n matrix. The very word you are able to understand, you will be able to that interchanging rows and columns. Not either way, in the sense not simultaneously, either rows into columns or columns into rows. Any one of them. Okay. So m by n matrix transpose matrix will be n by m matrix. That is, rows and columns are interchanged. So naturally, m by n will become n by m. Look at the symbol A superfix T. A superfix T. That is, capital T stands for the word transpose. Read A transpose. Don't read as A power T or don't read as A super T, but you read it as A transpose, but you write A and put the superfix capital T. That is the first row of A as its first column, the second row of A as its second column, and so on, as you know very well. So the row becomes column or the column becomes row, but uniformly have it in one way that change the row into columns. Okay. Thus the transpose of A is A transpose equal to, when A is AJK, it will be AKJ. For an example, if A equal to this much, then A transpose will be A11, A12, L, etc., A1N, something. This is the first row of capital A will become first column, A11, A12, etc., A1N. Similarly, as a special case, the transpose converts row vectors to column vectors and conversely. So here you just see that. So naturally, so you have here two rows and three columns, isn't it? So transpose, so it is of order 2 by 3. So its a transpose will naturally become 3 by 2. Is it right? So you have first row becomes first column, 5 minus 8, 1. Second row becomes second column, 4, 0, 0. Similarly, you can check. Now, rules for transposition. So the act of finding transpose can be called transposition, isn't it? Okay. A transpose, that is transpose of a matrix is A. Okay. Then A plus B transpose is transpose of addition of two matrices is addition of their transpose, sum of the transposes. That is A transpose plus B transpose. CA, that is constant scalar multiplication of a matrix for which you are taking transpose, is nothing but C into A transpose. Look at that. That's very important here. Okay. It is C into A transpose. Column, the constant scalar can simply be taken out from the entries of matrix A because that is being multiplied, this common constant, and A gets transposed. So CA transpose is nothing but C into A transpose. There is no transpose for C. It is just coming out, so it remains the same. AB transpose is not like your A plus B transpose, because in addition, the order is preserved. A plus B transpose is A transpose plus B transpose, or B plus A transpose is B transpose plus A transpose. But in the case of multiplication, transpose of product of two matrices is the product of the transpose of the matrices in the reverse order. It is B transpose into A transpose. All these things you can check with by taking simple matrices of order 2 by 2 of for A and B, product find and get say transpose done, and then go for B transpose. Already you are having A transpose, you can find, and then find their product. They will be equal. But the order is very important. AB transpose is B transpose into A transpose. Symmetric special matrices. Special matrices we are going to start now. Apart from your unit matrix and zero matrix, we have some more special matrices. Remember, all of them are square matrices. Symmetric matrix. When you will call a matrix A to be symmetric, if it is equal to its transpose. That is, row and columns are having the same elements. Just look at 20, 120, 200 first row, 20, 120, 200 first column. 120, 10, 150 second row elements, 120, 10, 150 second column. Similarly, third row, third column. So if the rows and column elements are the same, that is if A equal to A transpose, then such a matrix is called symmetric. Skew symmetric, Aij equal to minus Ahi. That is, a matrix A is said to be skew symmetric if the negative of the matrix is same as a transpose of A, or if it is equal to negative of its transpose. So skew symmetric. So look at here. One thing is very important. In skew symmetric matrix, the principal diagonals will all be equal to zeros, because you cannot have an element here whose negative is the same, isn't it? You cannot have, suppose you have first row, first column element 1, you cannot have the first row, first column element to be negative of it. Because they are different. So if at all you have an element which is the same, is by changing its sign in first row, first column, second row, second column, third row, third column. That is the principal diagonal elements. You will only be having zeros. Other elements you can have. Suppose you have 1 here, you can have -1. If it is -3, it will be 3. So you just look at now 0, 1, -3. So negative of the elements of the first row are the elements of the first column. 0, -1, +3. Second row, -1, 0, -2. Second column will be have +1, 0, +2. Third row you have 3, 2, 0. What will be the third column element? 3, -3, -2, 0. So it is negative of the elements, except that principal diagonal elements are all zeros. Then triangular, that is very, very important, because this is going to be useful in finding, reducing the given matrix into its echelon form, either upper triangular or lower triangular. There are two types of triangular matrices, upper triangular and lower triangular. Okay. So upper triangular means upper triangular. See, you just look at here, Aij equal to 0 for all I greater than j. And lower triangular Aij equals 0 for all I less than j. So this lives as a definition now, of course, which you can always verify, in the sense how you can easily remember without any confusion. In upper triangular matrix, above the principal diagonal elements, not all elements are zeros. Mostly you may have zero element, but there must also be non-zero elements. But necessarily below the principal diagonal elements, of the elements below the principal diagonal are all zeros for upper triangular. So upper triangular, that is above principal diagonal, you have existence of elements, but all elements below the principal diagonal will all be zeros. So that is what you mean by Aij equal to 0 for all I greater than j. For example, you just look at here. This is a 2 by 2 matrix. So this is the principal diagonal, isn't it? So here, this is A to 1. It is A to 1, isn't it? Aij is the second row, first column, A to 1. I is greater than j, A to 1. 2 is greater than 1, isn't it? So it is here. Look at this 3 by 3, which you quite often will be using in practice. You just see here, this is a principal diagonal element having elements 1, 3, 6. Below that, all of them are zeros. Now, you look at this condition now. This is A 2, 1, 2 greater than 1. A 3, 1, 3 greater than 1. A 3, 2, 3 greater than 2. So instead of remembering this way, you can easily remember that below the principal diagonal, all elements must be zero for upper triangular matrix. To have the upper triangular, you should have below the principal diagonal element zeros. In the opposite sense, for lower triangular, Aij equals 0 for all I less than j. In the sense, how you can easily remember, elements should exist below the principal diagonal element. Otherwise, the elements above the principal diagonal should all be zeros. Satisfy this condition. You just look at, you just take this 3 by 3. You have principal diagonal elements 2, -1, 8. Isn't it? Now, this is A1, 2. I is less than j. 1 is less than 2. 1 is less than 3. 2 is less than 3. So, these elements are above the principal diagonal elements, which are all zeros for a lower triangular matrix. Similarly, for a 4 by 4 matrix. Okay, right. Then diagonal matrix. Aij equal to 0 for all I not equal to j. Diagonal matrix means you will only have principal diagonal elements exist, not all zero. There may be a 0 or 2, but very rarely, but it must be a non-zero. So in the diagonal, not all of them are zeros. I not equal to j. Okay. That means for all I not equal to j, you have A12. For suppose you take a 3 by 3 matrix. A12, I not equal to j, A13, 0, 0. Here, A21, 0, A23, 0, A31, 0, A32, 0. So except the diagonal elements, other elements are all zeros. Except that's the reason why it is called a diagonal matrix. Diagonal should exist. Now you may have a doubt. Can we have at least, not at least, can we have one zero in the principal diagonal? Yes, you can have, but not all zeros. Okay, right. But necessarily all other elements except principal diagonal should be zero. Then scalar matrix. Aij equal to 0 for all I not equal to j, and Aij equal to c for all I equal to j. So such a diagonal matrix, if you are multiplying by a constant, if you are having a constant, a fixed constant, then it is a constant matrix. That is a scalar matrix. That is, you are having, see, if your entries are here, 2, as I just say, 2 minus 3, 0. Even in the, see here, the diagonal matrix, I just mentioned. In the principal diagonal, you may have 0, but necessarily elements below the principal diagonal, above the principal diagonal should be zeros. Scalar matrix, it is also a kind of diagonal matrix, but in the diagonal, you must have the same constant. You must have the same constant. Then it's a scalar matrix. Then unit matrix, which I already mentioned, it is also a diagonal matrix where each element should only be 1 and remaining elements are zeros. Okay. Now, okay, these are all you can easily find out. A, B, C, D. Find the following expressions: 2 times A plus 4 times B, then 7 times A, 0 times B, so that you get a zero matrix. This is A, B, you can find product, and then C plus D you can find. They are of same order. Then minus 2 into AB, the product. All these things you can try. And then CD, the product of these two matrices. So all these things can be tried. Now, next we pass on to finding row echelon form, row reduced echelon form, rank of a matrix using this concept, and using which we will be finding solution to system of equations. Well, row echelon form of a matrix. It is naturally row echelon, but we will be in practice be reducing it to row echelon form. Okay, see, the first non-zero element in each non-zero row is unity. So here are 3 rows. In each non-zero row, what do you mean by non-zero row? What is meant by 0 rows? Because that is going to be useful in finding the rank of a matrix. This concept of non-zero row. So here there are 3 rows, but there are only 2 non-zero rows. Be careful in identifying. Say here is a row, second row, having elements zeros, but there is one non-zero element. So this is a non-zero row. Only when all the elements of a row are zeros, it is called a zero row. Okay, so there are 2 non-zero rows. Okay, here is a 0 row. So what is the condition? The first non-zero element in each non-zero row is unity. So this is a non-zero row, first element is 1. This is a non-zero row, first element is non-zero element in each non-zero row. First element, first non-zero element, first non-zero element is unity, not any other number. It should only be unity. Okay, 0 rows, if any, right below the non-zero rows. Okay, this is a 0 row. These are non-zero rows. Okay. You can check this condition, the same condition here. This is a non-zero row. The first non-zero element in each non-zero row is 1, right? So this is the first non-zero element, which is unity in the second non-zero row. This is, of course, zero row, no problem. Then the elements below the non-zero element should be zeros. That is non-zero, the same thing. Zero row must be below the non-zero rows. Anyway, in practice, we will only be reducing into row echelon form. Well, similarly, we can do column echelon also, but it is easy to do uniformly. Let us fix it as reducing row wise by doing elementary row operations. We will reduce it to row echelon form and we will go for finding the rank. Look at what is rank of a matrix. The rank of by this is a classical definition as it is. The rank of a matrix is the order. Rank means it's a number. Is the order of the largest non-zero minor. See, by order, actually, you may wonder. See, suppose, see, minor means, of course, you will find a particular, suppose you have a 3 by 3 matrix. And for the first row, first column element, its minor is deleting the corresponding row and column, you have your 2 by 2 matrix, for which you take the determinant. Okay, determinant value, isn't it? So it is of order 2 by 2. But you will get the by order here, it is only going to be square matrix. So square matrix means the number of rows and number of columns equal to 0. Are the same. Number of rows are equal to number of columns. So don't multiply, don't say 2 into 2, 4. It is the number of rows. Means within brackets are the number of columns because they are the one and the same. So rank of a matrix is the order of the largest non-zero minor of A and is denoted by, look at the symbol, and this is a Greek symbol, Greek alphabet. You might have heard, you might have used to be pronounced as row of A. And some authors use a small r for rank also. Okay, according to this author, we will use the symbol row. In other words, a positive integer r is said to be the rank of non-zero matrix A if there is at least one minor of A of order r which is not zero, and every minor of A of order greater than r becomes zero. So this is a classical definition that you will first find the determinant should be non-zero. Suppose you have a 3 by 3 matrix. Find its determinant. If it is non-zero, what is the order of the matrix? Order is already 3 by 3. So what is the number of the rows? 3. So that is the row. That is the rank. Suppose the determinant value is 0. You go for a sub matrix, square matrix naturally. Naturally, it will be of order 2 by 2. For any element of the 3 by 3 matrix, even if there is at least one non-zero minor, then that gives the number of rows gives the rank. So anyway, but in practice, this is a classical definition that you might have done in your school days. But here, according to this, the syllabus content that you are expected to use this method to find the rank of a matrix by reducing the given matrix into row echelon form. Okay, so that is what you are expected to do it, not by finding the determinant value and go for non-zero minor. Okay, that is a classical definition. Okay, well, that is also true. But here you are expected to use this echelon form, getting it, reducing it to echelon form and finding the number of non-zero rows that defines the rank of a matrix. Look at the definition. The number of non-zero rows in the row echelon form of a matrix gives the rank of A and is denoted by row of A. Note, row of A greater than or equal to 0. See, only for zero matrix, row equal to 0. Otherwise, in general, row of A is greater than 0. And the minimum row will be, rank will be 1. Okay. Right. So if A is a matrix of order m by n, suppose you have a matrix of order m by n. You can find rank of a square matrix, rank of a rectangular matrix. It's of any order m by n. Then what will be the you cannot go wrong if you just know this concept, this axiom that row of a then its rank will be less than or equal to minimum of m comma n. So you have number of rows, comma number of columns. Minimum of those two numbers will be your rank that you can check. The rank of a zero matrix is zero. Okay. The rank of a non-singular matrix of order n by n is n. What do you mean by non-singular matrix and singular matrix? A matrix is said to be singular if its determinant is zero. Non-singular if its determinant is non-zero. Okay. Let's go for finding practical examples of finding rank of the given matrix. Example 1. Find the rank of the matrix A, where A equal to a 3 by 3 matrix is given 1, 2, 3, 2, 3, 4, 3, 5, 7. Okay, first let us have some impression. The order of A is 3 by 3, therefore we cannot exactly say what is the rank of A that we are going to find. But one thing we can visualize, we can commit that it is less than or equal to 3 because order is 3 by 3. So row of A is less than or equal to 3. It cannot be more than 3. Less than or equal to 3. Okay. It cannot be 0. It's a non-zero matrix, isn't it? So it can be 1 or 2 or 3. Anyway, it is less than 3 or equal to 3. Less than or equal to 3. At the most, it can be equal to 3. Let's see. So what is the exact answer? Row of A less than or equal to 3 is not the answer. That is only that we commit in the beginning, but we need to exactly check. Let us transform the matrix A to an echelon form by using elementary transformations. You know what is meant by elementary transformation. You can add one row to another row. See, you can do elementary operation row wise. You can do elementary operations column wise. Let us uniformly fix by doing elementary operations row wise. Okay. Let us uniformly do it. So let first A matrix A you are writing matrix. First you write the data. Then we are putting a symbol like this. A wave-like symbol means is equivalent to, because this matrix is not equal to this one. You must be knowing there is a difference between is equal to is equivalent to. Okay, it is only equivalent to, it's not equal. Anyway, we are only reducing it to echelon form, so is equivalent to. So don't put equal symbol, use the symbol wave is equivalent to. Now fix the first row. Fix the first row. So I would even rather suggest here elementary transformation. Of course, what are the transformations that are taking place? You can take it as a title and then write. Otherwise, even if you don't put any title here, you can just write here alongside. Okay. Here, I would suggest, since it is given as a separate column, not necessary. You can write here itself, but nothing wrong in writing. First, you write this one. R1 is R1. R1 is R1. What's the meaning? We fix R1 as it is. Okay. Now go to second row. First you fix always R1. Okay. Then go to second row. Well, what if 0 is coming in the very first element in the first row? We will interchange. Let us come to it later. So if you find the first row, first call element is a non-zero, then you fix it. R1 is R1. That is, you put an arrow mark, you write the same. Go to the second row. The first element should become 0. You know very well in ready echelon form, in the second row, first column element must be 0. In the next operation or operations, if need be, the third row, first column element, third row, second column element. That is below the principal diagonal elements, you must have zeros. So that we are reducing the given matrix into an echelon form, particularly upper triangular matrix. Echelon form means it can be upper triangular matrix or lower triangular matrix, but we will do uniformly row elementary operations on the given matrix to reduce it to upper triangular matrix. Okay, right. So what should we do? This should become 0. That is, second row, first column element should become 0. But how will you do? You have to do a elementary row operations on these elements, elementary operations on the elements of the second row with that of the first row, because the first row is fixed. How will you get 0 here? 2 minus 2 into 1. So in elementary operation, you can multiply by a scalar, a row or any column. Of course, we concentrate only on row uniformly. And then you can add one row with another row. Or you can multiply a row, every element of the row by a constant and then add to the other element. Or you can subtract one row from the other. All these things are called elementary operations. Okay, using basic arithmetic operations, scalar multiplication, addition, subtraction. Okay, right. So here, this should become 0 means 2 minus 2 into 1, 0. So only that you fix it. And that operation you do for every element of the second row. So that is what we mean by elementary row operation. So that is being done for second row. So R2 arrow mark, R2 is to be transformed as, our new R2 is obtained from this elementary row operation. What is that? Existing R2 minus 2 times R1. So you have to only check the first elements and this should become 0. How? 2 minus 2 into 1. That is second row element minus 2 times first row element. Makes it 0. Means you need to do uniformly to all elements of second row minus 2 times elements of the first row. That is what we mean by elementary row operation. In such a manner that it becomes 0. Not any way that we like. So 2 minus 2 into 1, 0. 3 minus 2 into 2, 3 minus 4, minus 1. 4 minus 2 into 3, 4 minus 6, minus 2. That is what we mean here. R2 is R2 minus 2, R1. Now, we need to go to third row. First column should become 0. So here for third row, first column element is 3. Now, you go to the same R1. But normally what we do, after having found R2, okay, we go to third row because already R1 is fixed. R2 is newly obtained. The same way R3 is to be obtained in terms of R1 again. That is fixed. Is it right? So you have for the first column. Okay. So 0 you must get means 3 minus 3. How will you get 3 here? 3 into 1. So that means that means the elements of the third row minus 3 times elements of the first row. You are getting the new third row. Isn't it? So how will you write this? R3 is R3, that is existing R3 minus 3 times R1. That is 3 minus 3 into 1, 0. 5 minus 3 into 2, 5 minus 6, minus 1. 7 minus 3 into 3, 7 minus 9, minus 2. That's all. This is one set of elementary row operations. Now, what is left? Second row, first column is 0, done. Second row, third row, first column is also 0, is done. At one stroke, we are able to do by doing elementary row operations on R2 and R3. As far as first column elements to become 0, keeping R1 fixed. Now, we need to also change the third row, second column element 0. Okay. Already R1 is fixed. No problem. R1 is R1. If you want, you can write. Now, we are talking about second column of third row. So, already R1 was used twice and two elementary operations were done. Now, coming to the third row, second column element, now that R2 can be fixed and we can do the second set of operation of R3 on R2 only. So, R2 is also R2. Yes, R2. R2 is R2. So look at 1, 2, 3. You have to take the latest one. Forget about the given initial one. 1, 2, 3, 0, 1, minus 1, minus 2. Keep it. So R1 is fixed. R2 is fixed. R1 is already there. Okay, so then this is okay, right. So now this should become 0. This element should become 0, isn't it? So what should you do? R2. Now you are going to the third row, second column element. So go to the second row. So you do the elementary row operation on the latest row, second row. That is to be fixed now. Okay. So what you do, what are the connection between the second row, second column and the third row, second column? It is -1. This is -1. Only these two you must check. You must check. This is -1, this is -1. How will you get 0? -1 minus of -1. -1 plus 1, 0. That means you are subtracting the third row elements. You are subtracting the second row elements from the third row. Isn't it? So your new R3 is existing R3 minus existing R2. That is 0 minus 0, 0. -1 minus of -1, -1 plus 1, 0. -2 minus of -2, -2 plus 2, 0. Thus, you are able to get. Don't bother about this 0 now. As of now, our aim is to reducing the given matrix into echelon form. That is triangular form. That is, let us uniformly do upper triangular. So don't bother about the principal diagonal elements. Okay, you are able to get the upper triangular matrix, echelon form. In the process, definitely, automatically, 1 or 2, depending upon the type of operations that we do in reducing it to echelon form, will become 0 row. Yeah. Okay, so here is 1, 0 row. There are 2 remaining non-zero rows. So remember here is a row where there is a 0, but it is not a 0 row because there are non-zero elements. So it is a non-zero row. It is also a non-zero row, but it is only a 0 row. Therefore, how many non-zero rows are there? There are 2. That defines the rank of the matrix. So the number of non-zero that you need to write. The number of non-zero rows is 2. Therefore, rank of A is 2. So basically, we said row of A less than or equal to 3, which we are able to now find that rank of A is equal to 2. Is it clear to all? Is there any doubt? Is it clear to all? Hello?
Yes, sir.
Okay, fine. Right.
Sir, can you once again repeat how can we find the rank
Which
of
one?
the
Which one?
to find the non-zero row side too?
Yeah,
How
yeah,
can
yeah. Fine, fine, fine. Have you understood this elementary row operations of R2 on R1, also of R3 on R1, so that you have in the first column of second row and third row zeros. But it is not the end of it. You should also make the third row second column element should be 0, so that this time we are taking R3 and we are making the latest R2 to be fixed. So we do one more exercise of elementary row operation. In the process, definitely not only we are making this is an upper triangular matrix, but also in the process automatically we are able to see, for example, so sometimes you may ask one question, sir, is it necessary that will it be like that when you do the second set of row elementary operations, in order to make it into echelon form, that is upper triangular matrix, suppose you get here some non-zero number, what will be the answer? What will be the answer? Suppose you may get a non-zero number here. Our aim is only to get 0, 0 in the first column, 0 in the second column of third row, here in the second row. So you may get the third row, third column element a non-zero number. In that case, how many non-zero rows are there? Can anyone answer?
two?
Hello? Yes,
I think it is
3.
two.
3. In that case, the rank will become 3. So it is not automatic. This element may be 0, may not be 0. If it is here, according to this problem, it so happened -1 minus of -1 So you get 0. Minus 2 here, minus 2. So minus of minus 2, minus 2 plus 2, 0. Supposing you are having different numbers, you may not get 0. It is not necessarily to become 0 because our aim is only to have below the principal diagonal elements to 0. That is the reason why we do two sets of elementary row operations to reduce the given matrix into echelon form. So in the process, you are finally able to see that according to this question, that there is one non-zero, there is one zero row and there are two non-zero rows. Therefore, the rank of A is 2. Suppose here you get a non-zero number, this will also become, despite the fact that there are two zeros, even if there is one non-zero element, this will also be considered as a non-zero row, so that this matrix will have three non-zero rows so that its rank will be 3. Is it clear now?
Yes, sir. Got it.
Fine.
Yes.
Okay, good. Same way. Just quickly look at. So here is a matrix of order 3 by 4. So rank of A less than or equal to 3 because minimum of 3 comma 4. Minimum of 3 comma 4. So less than or equal to 3. We are not sure. We are going to check. So matrix A, elementary transformation, R1 is fixed. Now, here one thing is, that's the reason why this problem is chosen as an example to highlight what I meant in the previous problem itself, that what if you get 0 in the very first row and column? You cannot fix it and do elementary row operation on it. Only when the first row, first column element is non-zero, you can do the elementary row operation on it. So you can do an operation only on a fixed one. Already there is 0, so you cannot do it. Therefore, in such cases, what you need to do, you can interchange the rows. By interchanging rows, we don't just mean only first and second should be interchanged. It can even be first and third, but it will confuse you. Okay, if you do so much of understanding. So better you can simply do interchange the first and second row so that the second row can be a fixed first row where the first row, first column element is a non-zero number. So R1, look at the arrow mark. There is a two-way arrow mark. That means R1 and R2 are interchanged. In the sense, R1 becomes R2, R2 becomes R. Is it right? So that is elements. Elements of R2 become elements of R1 and elements of R1 become elements of R2. You write the third as it is. So now we have only rewritten capital A by interchanging the first and second rows for the reason that we want the first row to be fixed with the condition that first row, first column element should be non-zero. Well, we will do now. First row is fixed. Now go for here. One thing is important. Now second row, first column must be 0, isn't it? That is already there. So one change of, that is one elementary row operation of R2 on R1 is saved. Don't do it again. Suppose you are doing it here, what will happen? 0 minus 1, minus 1. You will get minus 1 here. You should get 0. It's already there. So that operation of R2 on R1 is not to be done. It's already there. So go to third row. Look at the first column element, 3. Remember R1 is fixed as before. So here one row change is done, but elementary row operation is not done for the reason that it is already 0. Okay, so go to the third row, first column element. Go to the first row, first column element. Look for when it becomes 0, this should become 0. 3 minus 3 into 1. So your R3 is, so there is only one elementary row operation of R3 on R1 as R3 is 3 into R1. 3 minus 3 into 1, 3 minus 3, 0. 1, you have to be careful about the selection of elements of row in question on which you are doing the row operation. 1 minus 3 into 2, 1 minus 6, minus 5. 1 minus 3 into 3, 1 minus 9, minus 8. 3 into 3 minus 3 into 2, 3 minus 6, minus 3. So one set of, actually we will do two operations, but one we don't need to do because already there is 0. Now we have to go for making the third row, second column element is 0. which can be done by taking the third row now, and R2 is now fixed. R2 is fixed. Okay, so you have to do the elementary row operation of R3 on the immediate R2. That is the latest. Okay, so 0, 0, 0 is there. Here you have to take only for the second column. -5 is here, 1 is here. So how will you get 0 here? -5 plus 5 into 1. So that is to be done for all the elements of the rows. So R3 is, new R3 is existing R3 plus 5 times existing R2. So that is to be done for all elements. You start with the first row, first column itself, 0 plus 5 into 0. You should get 0 only. If you get something else, then you are wrong. -5 plus 5 into 1. -5 plus 5, 0. -8 plus 5 into 2. -8 plus 10, you get 2. -3 plus 5 into 1. -3 plus 5, you get 2. Now you look at, unlike in the previous problem, the last row is not becoming 0 row. There are non-zero elements. Isn't it? So there are 1, 2, 3 non-zero rows. Therefore, row of A equal to 3. Is it clear now? Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay. So linear system of equations. Now coming to finding solution of system of equations. Before that, we will also be checking consistency and inconsistency of a system of equations. What do you mean by system of equations? When you have a finite number of set of equations, it is called a system of equations. And how do your system of equations can be made into a general form so that it is going to be put into use by making matrix multiplication in a suitable manner. So in such a way, our equations are going to be written. And what is meant by linear? Linearity means degree of the equation is 1. That is, every variable in an equation is having a maximum power 1. Then that equation is said to be of degree 1. For example, you have x square. Suppose you have ax square plus bx plus c equal to 0. You know very well it is a quadratic equation in one variable x. Is also in general a second degree equation. It is not the number of variables that matter, but the maximum power. Ax square plus bx plus c equal to 0. X power is 1 in the second term. X power is 2 in the first term. So the maximum power of the variable in which the equation is written is 2. That is, degree of the equation is 2. So it is non-linear. Suppose you have the equation of a straight line of the form y equal to mx plus c, or ax plus by equal to c. You have an equation in two variables. Okay, but what is the power of x? 1. A into x power 1, that is ax, plus b into y power 1, that is by, equal to c constant. It can be 0 or any constant. Okay, so each of the variables in any equation is of power 1, so that the degree of the equation is 1. Such an equation is called linear. If not linear, it is non-linear. It may be of any degree, 2 or 3, anyway greater than 1. Such of those equations in general will be called non-linear equations. Then you can classify second degree equation, third degree equation, and so on. So anyway, our cup of tea is now to consider linear system of equations. So what is the form that we are making? There are suppose unknowns in the sense whose values are to be found, variables, x1, x2, etc. is a set of equations of the form. How do we take it in the form? A11 x1 plus a12 x2 plus etc. plus a1n xn equal to some constant b1. A21 x1 plus etc. plus a2n xn equal to b2, etc. etc. am1 x1 plus etc. etc. plus amn xn equal to bm. So we have m rows, n columns. So that matrix is going to be used. Rank of matrix is going to be used. For that, we have set of equations, a system of equations. Each equation is linear, so it is called a linear system of equations. That's what here we have got the description. The system is called a linear because each variable xj is appearing in the first power only. That is, it has got maximum power 1. So a11, etc., amn are given numbers called the coefficients of the system. Because you know very well, ax plus by equal to c, even though a, b, c are all constants, The constant that is in multiplication with a variable is called the coefficient of the variable. When you say ax, a is the coefficient of x, even though it is a constant. B is the coefficient of y. C, we don't say coefficient, it is purely a constant because it is not in multiplication with any variable. So we call it as simply a constant. So here, these are all a11, a12, etc., amn are called coefficients, isn't it? Because coefficients of x1, x2, etc., respectively. B1, B2, etc., Bm on the right are simply constants. If all the Bj are zero, the right hand side constant, then the system is called a homogeneous system, otherwise called non-homogeneous. Okay. If in a system of equations, say there are m equations or n equations, whatever it is, if all the constants on the right hand side are zeros, then the system is called a homogeneous system of equations, otherwise non-homogeneous. In practical problems, mostly we will be considering we can also encounter homogeneous system of equations having zeros in the right hand side, and non-homogeneous also we will be considering mostly. Okay, right. Look at when you have the linear system of equations of the form 1, we will refer to as equation 1 because the whole set of equations, every time instead of saying this, we can say the whole thing can be this is a system of equations or set of equations. We will use the word system. Refer it by equation 1 hereafter. Okay. Now, matrix form of the linear system 1. So we are making some matrix form. What is that? How are you able to do? Just see. From the definition of matrix multiplication, we see that m equations of 1, you have a11, a21, etc., am1, may be written as a single vector equation ax equal to b, where the coefficient matrix A is the m by n matrix. Capital X and capital B are column vectors. What is the meaning? If you just go back, you can first coin A11, etc., A1n, A21, etc., A2n, etc., AM1, AMN to be elements of a matrix A. And these elements are all nothing but coefficients. So it is called a coefficient matrix. Then you have x1, x2, etc., xn. That is going to be a vector, in fact, a column matrix denoted by capital X. And the right hand side constants will be denoted by a constant matrix, capital B or small b bold, because it's a vector again, column matrix. You can put either capital B itself or small b bold, nothing wrong. Whenever there is a vector, which we already have been familiar with the symbols. Okay. So thus this product, if you do the summation, if you look at, they can be classified as this set of equations can be written as AX equal to B. Is it right? You just check. AX matrix multiplication. This is of order m by n. This is of order n by 1. M by n, n by 1. N and n are the same. So m by 1. That means the resulting matrix will have m rows but only one column. So what is that? M rows and one column. This is m rows and only one column because you are doing the addition. Don't take it as m by n. A11 x1 plus etc. A1 m xn first row. A21 x1 plus etc. A2 second row, etc. You have m rows, but only one column, and therefore you can think of this A11 x1. How do you do the multiplication? A11 x1 plus A12 into x2 plus etc. A1n into xn. So that is the first row, only one element. Now Ax equal to B, corresponding entries are equal. So your B is matrix of constants. This is matrix of coefficients. This is matrix of unknowns. This is matrix of constants. Now equal to Ax equal to B, that is A11 x1 plus A12 x2 plus etc. plus A11 xn equal to B1. A21 x1 plus A22 x2 plus etc. plus A2n xn equal to B2. Similarly, etc. AM1 x1 plus AM2 x2 plus etc. plus AMN xn equal to BM. That is what your equation system of equations 1 is all about. Therefore, this linear system of equations 1 can be thought of a matrix equation in the form of Ax equal to B, where capital A is matrix of coefficients, X bold or capital X can be thought of constant column matrix, or if it is bold X, it is a vector having one column elements x1, x2, xn, which are unknowns to be found. That is going to be the solution of this system of equation using the right hand side constant matrix. Okay, so A, you can put the symbol wave overhead, and it will be called augmented matrix. You know very well, augmentation means you add, you enhance something, you improve upon something, you add here. Some authors use, instead of this one, they will write here, I will put this capital A, comma, because you are augmenting, you are adding. Adding means not summation. You are also joining it, rather. Augmenting is joining. Okay, you are taking into consideration A bold or capital B, whatever it is. Okay, this you put within square brackets. Well, see, that is, you can think of A, if at all you are using capital X, is equal to capital B. Then augmented matrix is matrix of coefficients A, comma, the constant matrix capital B. So you put it within brackets. If you are using bold B, small b, for since it's a vector, you can use B also, but bold it. Similarly, if you are using small x, then you have to bold it to mean vector. Anyway, both of them are okay. Matrix means capital letter. If you, since they are column matrices, they are being regarded as vectors. Therefore, you put small letter with boldness. So it's called the augmented matrix of the system one. So a solution of linear systems of equations. So we will find the solution. What types of solutions we can think of? Unique solution, infinitely many solutions, and no solution at all. Then that will lead to the concept of consistency and inconsistency of the system of equations. It's already 6:19. So I think I can stop sharing here itself. Of course, we just have 3 more. It is not just the coverage of number of slides, but it is the topics, contents that are to be covered without missing them. Anyway, I will just take it up in the beginning of the session to start again with the solution of linear system of equations, complete, and then go for its continuation in the next session. What are the contents are to be covered in that session? Okay, is it okay? Is it okay?
Yes, sir.
Okay, because it's already
Yeah,
6:20.
sir.
Therefore, okay, therefore I can stop sharing. If you got any queries, you are welcome to ask me. I will be happy to clarify. If no, then I can stop sharing. I can leave the meeting. Anything? Anything you want to say? Any clarification you want to seek? Any one of you? If there is no
No,
query,
sir,
then
nothing. No
okay. Have you
query,
all
sir.
understood? Have you all understood? Is it okay?
Yes, sir.
Okay. Is the pace of delivery is okay for you? Or if you
Yes,
want
sir,
me?
it is all good.
Okay, fine. So you don't want me to go any fast or slow? Is it okay?
Yes,
I
it is
expect it being
perfect.
there.
Thanks, sir.
Yeah,
Yeah, sir.
fine. Thank you. Okay, thank you all. Thank you then. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Okay, thank you, sir.
Thank you. Thank you, one and all. Thank you, one and all.